I wish to pursue graduate study at Courant because it has been a hotspot for great applied math research ever since many decades ago. The mathematician that appeared multiple times in my PDE numerical analysis course, Peter Lax, was once the director of Courant. This is not to even mention the other two great former directors, including the founder of this very institution, Richard Courant and Kurt Friedrichs. Their names are part of the famous CFL condition. For some of the more recent great mathematicians, I know of Andrew Maggia, who was the doctoral advisor of Andrew Bertozzi, the principal investigator of our research team at UCLA. Also, when I attended the APS-DFD conference in November, I had a nice opportunity to listen to Michael Shelley's invited talk on self-organizational phenomena in growing egg cells. I thus have very high regard for all of the researchers at Courant and eagerly wish to follow their footsteps and conduct influential work for math and society. This is why I want to go to Courant. I also realized that doing a math PhD at Courant could help me achieve my future goals. I love research. As I noted in my statement of academic purpose, I am thrilled by scientific discoveries and welcome the challenges that come with making these discoveries. I'm specifically interested in applied math because I know it can contribute usefully to other sciences, such as biology and physics, which I also like and have been doing some work on. I appreciate the quote, "Mathematics is the queen of sciences." So I wish to do all that stuff at Courant. I want to study differential equations that could model such natural phenomena and integrate theoretical analyses and computational methods in addition to necessary experimentation. This is also what I want to do after graduation. I desire a researcher position in some institution like a university or a national lab. I think that a Courant degree can most definitely help me excel in my future work. Now I want to present to you some mathematical subject that I find very elegant, which is complex analysis. And one of the nicest theorems in this discipline, I think, is Cauchy's integral formula. So the statement is, if you have f, a holomorphic function, on an open set U of C, with this closed disk belonging to U, and if you have this parametrization of a circle, then for any point that lies in the interior of the circle, the function value at that point is going to be equal to 1 over 2 pi I times the contour integral over the circle of this integrand. So this is a very surprising result. It's like f in the interior is completely determined by the stuff on the outside, on the boundary of the circle. Our complex analysis instructor, Robert Green, told us it's like if you walk around the outside of a building, then you know exactly what's going on in the inside. This sounds quite unlikely in real life, yet it works in a complex world. So when I first saw this theorem, I couldn't help but admire the simplicity and beauty of it. And even more pleasurable is that there are a couple more such nice things in complex analysis. Liouville's theorem, maximum modulus principle, and the Riemann mapping theorem. And all these things deepen my love for this subject, and of course, math overall.